All right, today we're going to tackle a topic that can really rewire your brain when it comes to solving problems. We are talking about recursion. It's this powerful idea in programming that honestly feels less like just writing code and more like teaching the computer how to think on its own. It's a huge shift in perspective, so let's dive right in.
You know, this quote really nails it. The whole idea is, instead of trying to solve some huge, messy problem in one go, what if you could just ask the same question over and over, but on a smaller piece each time? That's recursion. It's this super elegant way of thinking that, once it clicks, makes these really complex algorithms suddenly feel, well, simple.
Okay, so here's how we're going to break this down. First, we'll get into what recursion actually is. Then we'll look under the hood at the engine that makes it run, the call stack. After that, we'll talk about the mental shift you have to make, when you should and shouldn't use it, and finally, how to keep your programs from crashing. Sound good? Let's go. So, first things first. What is recursion? At its absolute core, it's just a function that calls itself. Yeah, that's it. Imagine you're reading a recipe, and one of the steps is, now go back to the beginning of this recipe. That's kind of the vibe. So, to be a little more specific, it's a process where a function calls itself to solve a smaller version of the very same problem. The key words there are calls itself and smaller version. The best analogy I've heard is those Russian nesting dolls, you know? To find the tiniest doll, what do? You open one and you find a slightly smaller identical doll inside. You just keep repeating that exact same action until, boom, you hit the last one. That is the recursive mindset. Okay, but wait, if a function just keeps calling itself, wouldn't it, go on forever? Well, yeah, it would, and that's why every single recursive function must have two parts, no exceptions. Part one is the base case. This is your stop sign. It's the condition that tells the function, hey, you're done, stop. Part two is the recursive case. This is where the magic happens. It reduces the problem just a tiny bit and then calls itself again. And I can't stress this enough. That base case is absolutely critical. If you don't have one, the function just calls itself. And again, forever. It's like an infinite echo in your code. And your computer, trying to keep track of all those calls, eventually just runs out of memory, and your program crashes. Hard. So the number one rule is always have an exit strategy.
So you might be wondering, how on earth does the computer keep track of all of this? I mean, a function is in the middle of running, and then it calls itself. How does it not get totally lost? Well, the answer is a really cool mechanism called the call stack.
I want you to picture a stack of plates at a diner, right? Every time a function gets called, the computer puts a new plate on top of the stack. This plate is actually called a frame, and it holds all the important info for that one specific call, like its variables and where it's at. Let's make this real with a classic example, calculating the factorial of 3. So, first we call factorial of 3. Boom, a plate for factorial of 3 goes on the stack. But factorial of 3 can't solve itself yet. It needs to know what factorial of 2 is. So it calls it. And what happens? Boom, another plate for factorial of 2 goes right on top. And that one calls factorial of 1. So, you guessed it, another plate gets stacked on top. And now, right here at the very top of our stack of plates, this is where everything changes. The call to factorial of 1 finally hits our base case. It's the simplest version of the problem, and it knows the answer. It doesn't have to call itself anymore. For the very first time, one of our functions can actually return a real value. And just like that, the whole thing goes into reverse. The top plate, factorial of 1, is done. It gets popped off the stack, and it hands its answer down to the plate below it. Now factorial of 2 has the info it was waiting for, so it can finish its job, pop off, and hand its result down. The stack just unwinds one plate at a time until that very first call at the bottom, factorial of 3, finally gets the answer it needed all along. And this brings us right back to that crash we talked about. You've probably heard the term stack overflow error. Well, this is it. It's literally what happens when you try to stack way too many plates. If your function just keeps calling itself, the stack just gets taller and taller and taller until it runs out of space in the computer's memory. And that's when it all comes crashing down. So, understanding the call stack, that's the how. That's the mechanics of it. But the real secret to getting comfortable with recursion, it's a mental shift. You kind of have to stop thinking like a human and learn to start thinking a little bit more like the computer does. See, we humans, we like to think step by step. You know, do A, then do B, then do C. It's a nice straight line. But a computer running recursion, it thinks in layers. It's more like it starts task A,
pauses it, starts task B right on top, pauses that, starts task C, and only then does it start finishing them in reverse order. C, then B, then A.
Now, this next part is maybe the most important thing you'll hear about recursion, so listen close. You have to stop trying to trace every single function call in your head. It will drive you crazy, I promise. It's just too much to juggle. Instead, just focus on two things. One, get your base case right. That's simplest possible answer. And two, make sure your recursive call is getting one step closer to that base case. If you do that, you just have to trust that the function will work. You reason backwards from the stop sign, not forwards into the chaos.
All right, so we've got this tool that's super powerful, but also kind of dangerous. So the big question is, when should you actually reach for it? Let's figure out where recursion really belongs. When we compare recursion to a standard loop, you see some clear trade-offs. Recursion can be incredibly elegant. For problems that branch out, like exploring a file system or a family tree, the code can be beautiful and easy to read, but it uses more memory because of that call stack. Loops are your workhorses. They're super efficient, they don't use extra memory, and they're way safer from crashes. They're perfect for straightforward, repetitive tasks.
So here's a good rule of thumb to go by. If your problem looks like a tree, with branching paths where each choice leads to more choices, then recursion is probably a great fit. The code will actually look like the problem you're solving. But if your problem looks more like a straight road, just counting from 1 to 100 or going through a list one by one, just use a loop. It's simpler, faster, and safer.
Okay, last thing. Let's talk about how to avoid the crash, because knowing the common mistakes is the absolute best way to make sure you don't make them. These are the big 4 traps people fall into. Number 1, the most obvious, you just completely forget to write a base case. Number 2, you have a base case, but your logic has a flaw, so you never actually hit it. Number 3 is a sneaky one. Your function calls itself, but it doesn't actually make the problem any smaller, so you're just spinning your wheels. And finally, you can do everything right, but the problem is just so big that you get a stack overflow anyway. So after all of this, the call stacks, the base cases, the risk of crashing, you might be sitting there thinking, what's the real point? Is this all just some clever code trick to show off? And the answer is a definite no. The point is actually much deeper. Learning recursion isn't about writing clever code. It's about learning how the computer thinks. It forces you to see problems not as one long to-do list, but as layers of the same small problem. And that way of thinking is fundamental to how so much of computation actually works. It's not just a new tool, it's a genuine upgrade to how you see code.